Let's go through what is called an equivalence relation. Now, equivalence relation is something generic for, not generic, but like it's used in a lot of different ways. So you've already been familiar with an equivalence relation. You just don't know it, maybe. So an equivalence relation is something that is reflexive, symmetric, and transitive. So you have all three of those, and then you call it an equivalence relation. So a simple one would be equality. So an equality that you know and love is an equivalence relation. So basically, if you had a number, I'll just show you this real quick. So if you had a number, say x, then you can say x is equal to itself. So you would say x is equal to itself. So that's reflexive. Reflexivity is another way of saying it. Symmetric would be like saying, and it's tough with equals because it's kind of saying the same thing, but it's basically saying if x is equal to x, then x is equal to x. It's like saying it implies that it's equal to. You can't flip an equation, so it's kind of hard to say it like that. But basically, it goes both directions in that case. And it'll make more sense with similarity. And then transitive is saying basically if x is equal to y and y is equal to z, then x is equal to z. That's transitivity. So for similar matrix, we have and I'm not going to leave this here because it's not a great example. But there's something you could easily look up. Just look up equivalence relations and online, and you'll see some better examples of that. Okay. So for similar matrix, we define that, and I use this little form thing here for similar. So P is similar to, so if P is similar to, or I'm sorry, P is similar to itself, that's reflexive. If P is similar to Q, then Q is similar to P, and that's called symmetric. And then transitive, if P is similar to Q and Q is similar to R, then P is similar to R. So that's transitivity. So it goes like that. Okay, so might be familiar with this. If you ever teach or tutor math for elementary school teachers, you will go through this concept as well. Okay, that's math 4 at JV, by the way. Definition. Okay, so let's define similar matrices. So, and I all this is written up this time. I just did it like that because there was just a lot here. So you may want to pause and do stuff as you go. And then my examples, this is number 18 in the book. And then I have more examples down here. So you may want to pause and do those. But I'll just go through these and describe it as we go here and as you write them up. Okay, so let P be an n by n matrix. We say P is similar to Q, and it's that direction we want to keep in mind. So P is similar to Q if there exists an invertible matrix C, and I left off some verbiage, but such that C inverse times P times C is equal to Q. Okay, so basically you have an invertible matrix where you multiply in that order and you get Q. And then these are then equal. So that's what we call a similarity. Okay, so next example is 16 in the book. It says show that similar matrices are an equivalence relation. So we're going to show that this property here, or I should say definition here, is an equivalence relation. So you want to show that there's reflexive, symmetric, and transitive. So let's take a look. So reflexive basically is kind of nice and simple because you just are going to find the matrix C such that you can put P on both sides and get the same thing. Well, basically you just use the identity matrix, and then that satisfies. That's your C. such that that's true. So it's similar to itself, right? So P goes here. So it is reflexive. And then symmetric, we want to let this be true. So C inverse PC is equal to Q. Now, basically all you got to do is manipulate this, multiplying both sides, left-hand multiplication and right-hand multiplication, and then you'll end up getting that P is equivalent to Q. So this statement right here is basically saying, let's see, that P is similar to Q. So you want to have the statement Q is similar to P. So that would be the other direction. Okay, and we are going to use the concept of equality being an equivalence relation as well, actually, in here. So, so basically what you got to do is you say this. I actually should have said that. You want to assume P is similar to Q, then you get this. Okay, that's definition. From that, you multiply both sides by C and on the left, and multiply both sides by C inverse on the right. So that will simplify to, where'd it go? Oh, well, Q's here, so C and C. All right, so then this is just P on the right-hand side, and then it's C, Q, C inverse. But C inverse inverse is what? C inverse inverse is C. Okay, so that's what makes this work. And so then it's the inverse of whatever is here. So the existence is, the C is C inverse. So you can call C inverse like D and it still works. And then just to put it in the right order, I flip this because that's the direction we like to say it. Although it doesn't really matter because you have, for an equation, you do have basically, it's reflexive. You can flip it. Okay, so the direction doesn't really matter here, frankly, because of the equality. But I flipped it anyway, like that. And then you have that Q is similar to P. Then transitivity, basically you set up two of those, and then you manipulate that. So you're going to take your, what's nice here is actually, in some ways it's easier. You take your Q, which is this, and substitute in. So you have H, and here's your Q, H, and then you simplify it. So you're using that one of those properties we had way back when, where if you have H inverse, C inverse, first we're doing associative properties, okay? So well, that's not the right one, but associate, okay, so here and here. And then you're using the property that says H inverse C inverse is the same as CH inverse. Okay, so here's your product equals R, and therefore P is similar to R. Okay. Then I put in a few examples, and I forgot to write down the actual question on that one. This is number 18. I'll look it up as I'm talking here, I guess. Let's go on to these examples. So this is 5.2. Okay, so take a look at 50. I don't know which ones I assigned. I just had these in my notes, and I just decided to copy them. So look at 5.1, 30, 5.2, 15, and 17. So try those, and I believe that 18 is, let me look at that. I think that's 5.2. Yeah, I think that is. I'll only take a second here, I think. Prove that similar square matrices have the same eigenvalues and the same algebraic multiplicity. Okay, so this is actually getting ahead of myself a little bit. So, but it's here. You can look at it. So this is referring to what I'm going to talk about down here. And here's some more examples that I wanted to throw in. These are right from the book. Diagonalizing a matrix. Okay, again, how to diagonalize. So you need to know how to diagonalize the matrix. So look at those examples. And then I did one here, small one by hand. So diagonalize the matrix A. So you got to find their eigenvalues, corresponding eigenvectors. And then your C are the eigenvectors. And the D is the diagonal of those vectors. And you then check the product. And so make sure you can diagonalize a matrix. It's one of those computational ones that you're guaranteed to have, more or less. All right, so this goes back to example 18. Algebraic multiplicity of an eigenvalue of A is its multiplicity as a root. So you get the polynomial, and then you could have, something like this. If you have lambda minus 2 cubed, and then lambda minus 1 squared, and then lambda plus 5, then it's basically lambda is equal to 2 with multiplicity, I call it P for multiplicity, is 3. Lambda is equal to 1 with multiplicity 2. And you have lambda equals negative 5 with multiplicity 1. So that's called the algebraic multiplicity. Okay, that's this part here. So algebraic multiplicity is that. The geometric multiplicity is basically has to do with the number of, by definition, it's the dimension of the eigenspace. So it has to do with the number of eigenvectors. Okay, so that's the number of eigenvectors is the geometric multiplicity. So I suggest, sorry, I was looking down if I had any more, that you go back to these examples to look that up. So example 4, let's see. I'm not sure that's it or not. Well, okay. 18 has to do with that. It has to do with similar matrices. So look up 18. This is 5.2, page 315. So go back and look at that. And let's continue here because I know I have it down here. I've been doing this for a little while. All right, so I'll be making up these notes for a little while. So one of the properties of the geometric multiplicity has to be less than or equal to the algebraic multiplicity. Okay, and then one of the next theorems is an n by n matrix is diagonalizable if and only if the algebraic multiplicity equals a geometric multiplicity. So it's like it matches. So remember the proof we did, or the hypothesis of a matrix being diagonalizable has to do with it has to have distinct eigenvalues. Well, if you have multiplicity greater than 1, it's not distinct. So they have to match. And there's a lot to there. I'm not going to spend a lot of time on it. I want you to kind of study it enough to get a feel for it, okay? We have a lot to do and want to keep going. This is, though, an important one that we'll look at more later. This is one of the reasons I like to go on to chapter 9, because you can prove this in chapter 9. Every real symmetric matrix, remember, symmetric matrix means that A is equal to its transpose, so it has symmetry to it, right? It's equal to its transpose. It's a square matrix. So every real symmetric matrix is real diagonalizable, meaning real eigenvalues on the diagonal. What's interesting, though, is you have to go into chapter 9, or for this book, I'm not sure have to is the case, but in this book, it's a lot easier to prove it in complex plane and then come back to the reals. It's like you go outside of your system, which is the reals, to show something, and then you'll make an argument to say, but those are all real numbers. And then so you come back to being real. So the proof, as the book states too, is in chapter 9. So we'll probably finish with that, I think, for the class. And you'll be able to show that this statement's true. So symmetric matrix, and being diagonalizable we didn't really talk about a lot, but it has a lot of important properties that allows you to work with a matrix a lot easier. And it's a common thread you'll see in math and physics, engineering, is to make complicated systems into something more simple. Bits and pieces of them are more simple to work with. And that's what this process is a lot about, at least the theory behind it anyway. Okay, so there's a lot here for a short video because I didn't write all this out. So please take your time to go through this. I will post this soon because I think we're done finally with chapter 5.